Now that we know some general rules for drawing Lewis structures or compounds, mainly the octet rule, let's see how you would exactly draw one if given a compound. So let's start with the compound NH3, commonly known as ammonia or nitrogen trihydride. What do you do first? Well, the first thing to recognize is the first atom listed in the compound, in this case ammonia, is usually the central atom. This just means it's in the middle. The exception is if it starts with hydrogen, hydrogen can't be in the middle. Because if it only makes one bond, you can't have it connected to multiple things. So the first atom listed, in this case nitrogen, is going to be in the middle. So the second step is we are going to write down the central atom and draw the other atoms around it. So that's going to look like, here's nitrogen in the middle, and then we'll draw our hydrogens around it. It's important to remember that because electrons surround these elements and electrons are all negatively charged, that the atoms are going to want to stay far away from each other. So try not to group all the surrounding elements all on one side. Try to spread them out as much as possible. So we've written down those elements. Next, we are going to determine the number of valence electrons in the compound. And you've actually done this before. We've looked at the periodic table and we've determined how many valence electrons something has. So off to the side we're going to write, well, nitrogen has 5 valence electrons, and hydrogen has 1 valence electron, but because we have 3 hydrogens, we're going to have 1 times 3 valence electrons, so we'll have 3 valence electrons coming from the hydrogen, which gives us a total of 8 valence electrons. So we have 8 valence electrons in this compound. Next, we're going to connect all of the atoms to the central atom with covalent bonds and complete the octets of all atoms using lone pairs. So this is going to be connecting each hydrogen to the nitrogen. And we're only connecting to the central atom. We're not connecting any of the surrounding atoms together, just to the central. And then it says, complete the octets by using lone pairs. So let's look at each atom. Hydrogen has 2 valence electrons, because remember, in a covalent bond, that represents 2 electrons. And these electrons are being shared, so this hydrogen has 2 valence electrons, and because it's hydrogen, 2 electrons is enough. Same thing for this hydrogen, it's sharing 2 electrons, so it has 2, and this hydrogen, it also has 2, so all of the hydrogens have complete octets. If we look at nitrogen, nitrogen has 1, 2, 3 bonds around it, each one containing 2 electrons, so it has 2, 4, 6 electrons around it. It needs 2 more to get up to 8. So we'll draw in those extra electrons as lone pairs. Now we have 2, 4, 6, 7, 8 electrons surrounding our nitrogen. So all of our octets are complete. The fifth step is we have to count the number of electrons in the drawing. We have to make sure that the number of electrons that we actually put here is equal to the total amount we have. If it's not, this drawing is not correct. So we'll count 2, 4, 6, 7, 8 valence electrons that we can see in our drawing. And this is equal to the 8 valence electrons that we counted that we actually have available to us to use. And so if these numbers match, in the drawing and in what was calculated from the periodic table, you are done. So we put our first atom, our central atom, in the middle. We drew our other atoms around it, calculated the total number of valence electrons that we should have using the periodic table, counted how many valence electrons there were in our image after we connected everything with single bonds and completed the octets with lone pairs. And once we see that the numbers of electrons in our drawing and from the periodic table match, we're good and we're done with our Lewis structure. Let's try another example. This time we'll find the Lewis structure of carbon dihydrogen monoxide. Carbon dihydrogen monoxide. So we'll start with rule number 1. The first atom, in this case carbon, is going to be in the middle. And then around it, we put our other atoms. Again, these atoms we're going to put as far apart from each other as they can because the electrons around them repel. Next, we have to determine the total number of valence electrons that we have from the periodic table. Carbon has 4. Hydrogen has 1, but we have 2 of them, so we multiply by 2. And then oxygen has 6 valence electrons, giving us a total of 12 valence electrons. So now we have to connect all of the atoms to the central atom with covalent bonds and complete the octet. Connected with single bonds, we'll look, hydrogen has 2 electrons from this covalent bond, it's good. This hydrogen has 2 electrons from this covalent bond, it's good. Carbon has 2, 4, 6 electrons around it, so it's going to need 2 lone pair electrons around it. And then oxygen has 2 electrons in this bond, so it's going to need 6 more to complete its octet. So it's going to need 3 lone pairs. So next I have to count the number of electrons in the drawing. So I have 2, 4, 6 from the bonds, 7, 8, 9, 10, 11, 12, 13, 14 when I include the lone pairs. So I have 14 electrons in my picture, but we'll notice that 14 is greater than the 12 valence electrons that I'm supposed to have in my image. So what do I do now? Well, we need another step. Step 7. If the drawing has more valence electrons than calculated from the periodic table, you are going to erase a lone pair from two atoms that are next to each other and replace those pairs with a double bond. So if the drawing has more valence electrons than calculated from the periodic table, we erase a lone pair from two atoms that are next to each other and replace those lone pairs with a double bond. What does this look like? Well, the only atoms that have lone pairs are carbon and oxygen. So we're going to have to erase lone pairs from these atoms. Now, hydrogen can never make a double bond, and it doesn't have lone pairs, so we don't have to worry about it. So we have one lone pair in carbon, so we'll get rid of those electrons. We'll also get rid of two electrons, a pair of electrons from the oxygen, and in their place, we're going to draw a double bond. I added another bond there. Let's look at what this does. So now I have 2, 4, 6, 8 electrons that are connected to carbon. So carbon still has a complete octet, and I have 2, 4, 5, 6, 7, 8 electrons around the oxygen, so I still have a complete octet. Once I do that, I repeat steps 5 and 6. So now step 5 is I count the number of electrons in my drawing. I have 2, 4, 6, 8 in bonds, 9, 10, 11, 12, including the lone pair electrons. So I have 12 in my drawing, and that equals the 12 that I counted from the periodic table, and I am done. If for some reason this number was still too big, then I would do number 7 again, and I would continue until my two numbers were equal. Let's practice with two final examples. The first one we'll look at is phosphorus pentachloride, PCl5. So we'll put phosphorus in the middle, and then we'll put the 5 chlorines around it. Once we've done that, we'll figure out the total number of valence electrons. Phosphorus has 5 valence electrons, and chlorine has 7, but we have 5 chlorines, so we have 35. So together we have a total of 40 valence electrons. So that's from the periodic table. We'll next draw single bonds between each of the atoms in the central atom, and we'll complete the octets. Each chlorine has 2 electrons from the bond, so each one needs 6 more. Phosphorus has 2, 4, 6, 8, 10 electrons around it, so it actually already has more electrons than it needs. But this is okay. This is called our expanded octet. So this is the example of the expanded octet. And if you end up with something with more than 8 electrons in the middle, that is okay, as long as you're following the rules that I showed you before, where you must be in the 3rd row or below for this to happen. Phosphorus is below that, so it can have an expanded octet. Let's count the total number of electrons. 2, 4, 6, 8, 10 from the bonds, plus each chlorine has 6 electrons in the lone pairs, so that's 30 plus 10 gives me 40 electrons in the picture, and that's equal to the 40 electrons that we should have from the periodic table, so we are done. So that's the example of the expanded octet. The last example that I'm going to do with you is Br, so bromine, penta, iodide. Bromine pentaiodide. In this case, bromine is going to be in the middle, with the 5 iodines around it. If I count the total number of electrons from the table, bromine has 7, and the iodines also has 7, but there are 5 of them. So 7 times 5 is 35. 35 plus 7 is 42 valent electrons. Next, I connect all my elements to the central atom with single bonds. Notice that here I also have an expanded octet, and I complete all of the octets with lone pairs. Each iodine has 2 electrons from the bond, so each one is now going to need 6 more. Now I have to count how many electrons are in my picture. So there are 2, 4, 6, 8, 10 electrons in the bonds. Each iodine has 6 electrons in the lone pairs. So in total, my drawing has 40 electrons. And this is less than the 42 that we had from the periodic table. So what do we do in this case? This time, if the drawing has fewer electrons than calculated on the periodic table, the extra electrons are added to the central atom. So in this case, because we have fewer electrons here than what we calculated on the periodic table, those extra electrons, the 2 more that we need, are added to the center atom. Again, this is okay because we are allowed to have an expanded octet. We'll now return to steps 5 and 6. We have 2, 4, 6, 8, 10 in the bonds, plus 32 electrons from the lone pairs. So now in the drawing we have 42, which is equal to the 42 electrons calculated on the table, and we are done with our Lewis structure. One more thing I need to show you with Lewis structures, though, is what happens if you have something with a charge. For example, a common ion you may see is the hydroxide ion, OH minus 1. Whenever you have something with a charge, you follow the same steps for your Lewis structure, where you figure out how many electrons are given in each atom from the periodic table. So oxygen has 6 valence electrons, And hydrogen has 1 valence electron, and this -1 charge here tells us that we actually have 1 more electron in our Lewis structure. So here our total is actually going to be 8 valence electrons instead of 7. If we have an ion with a positive charge, such as the ammonium ion, so that's N in the middle with H's around it, we figured out the total number of valence. Nitrogen has 5. Hydrogen has 1 times 4, gives us 4 valence electrons, and the +1 tells us that we actually have to subtract 1 electron from our total. So instead of having a total of 5 plus 4, 9 valence electrons, we actually have to get rid of 1, so we have 8 valence electrons in our compound. For both of these, because they're charged, I'm going to finish the Lewis structures right now. When we finish, we have to put our compound in brackets and put the charge on the outside. So I'll finish the ammonium. And again, because it has a charge, I put brackets around it and the charge on the outside. So just remember that when you have a negative charge, you have to add that many electrons to it. And if you have a positive charge, you have to subtract that number of electrons from the total number that you should have.